Okay. I guess we'll start. Thanks for joining, by the way. I know a lot of people are busy, so thank you for taking the time and joining this. So yeah, today we're gonna talk about Bitcoin. And my goal basically for this lecture is for you to have a basic understanding of how Bitcoin works. So we're gonna talk about mainly 4 parts of Bitcoin. So first identity, and then transaction, and then network, and then lastly blockchain. And then we'll conclude with some of the value of Bitcoin. So first, Bitcoin identity. So because Bitcoin is decentralized, right? So there's no place for you to, create an account, register for an account. So instead, what you do is you kind of have to create an account by yourself. So you basically do randomly generate a private key. So if you remember from the last lecture, we talked about private and public key pair thing. This is kind of similar. So you randomly generate it. Usually you use a software to do it. And let's see. Okay, so yeah, you randomly generate it, and this thing is 256 bits. So basically, if you are familiar with some computer science term, it's just 256 ones and zeros. And this is like your password, so you have to keep it safe. And this is kind of how you can represent it in 2 different ways. So this is how a normal private key will look like, as an example. And then public key. So once you have your private key, you use your private key to generate your public key using this algorithm that we kind of mentioned in the last lecture called elliptic curve digital signature algorithm. And what you do is basically have a way for the private key and public key to be related. And one key thing to note is that you cannot find the private key given a public key. So your public key is 512 bits, so it's longer than the private key. And this is an example of what it looks like. Okay, and then one more step. So you have your private key, you have your public key, and one last thing you need to do is to generate this address. So you can see it from the right over here, you have your public key, and it goes through a lot of steps and then finally generate this address. So this address is kind of like your user ID, where people can find you and send you Bitcoins. So there's an example. So again, you have your private key and then generate a public key, and then public key goes to something, public key hash and blah, blah, and then you have your address at the end. So to kind of summarize what we have so far, your private key is kind of like a password. You use it to redeem your Bitcoin. And then you have your public key, that's like your username, use it to receive Bitcoin. And then you have the address, kind of like your user ID, and then that's how you be found on the Bitcoin network so people can send you Bitcoin. So an advice here, a more secure way to do things is that you generate a new key pair each time you do a transaction, or you have like a new address each time for the transaction. And we'll talk about why in a little bit. So here's some questions that you might be asking. So what if I lose my private key? Or, what if someone stole my private key? Or even what if someone guesses my private key? Or even if not intentionally guessing, what if they randomly generated the same private key as mine, right? And the answer to those are, if you lose a private key, then your Bitcoin is gone forever. There's nowhere to recover it. If someone stole your private key, then they have complete access to your Bitcoin. So you just have to keep it safe. So what if someone guesses your private key, or they randomly generated the same private key as you? That is mathematically impossible to do that, just because the amount of possible private keys is so large. And just to give you an idea of how large a number is, the number of addresses possible is 2 to the fifth 160. So this number right here. So you have 2 to the power of 160 unique addresses that's possible to be generated. And just to kind of like comparison, there are 2 to the 63 grams of sand on Earth. So if you put that into perspective, if you have a 7.5 billion population, then each person can have 2 to the 117th addresses, which is a lot. So now what you have is all these keys and addresses, right? How do you kind of store them in this thing called wallet? So this is basically like a software that holds, and some of them also generates a private key for you. And this is how most people use to access your Bitcoin. So there are two types. One is called hot storage and the other is called cold storage. And the main difference is basically one is online and one is offline. So for hot storage, it could be a mobile wallet, it could be a web wallet that stores your keys. And then for offline, you could have paper wallet, like the one on the right. This is an actual Bitcoin address. So you can see here how you spend it. Here's your private key over here. You want to keep it safe. You don't want anyone else to see it. But on the left, you have your Bitcoin address. So here's the QR code that you let people scan to send you Bitcoin. There's also a hardware wallet, so like a USB stick that stores the information, and then also brain wallet, some methods that you can help yourself memorize the private key. So we talked about this in the last lecture, but just kind of review it. As a way to prove that you own your Bitcoin, you need to have this thing called digital signature. And the way to do it is, like we talked about last time, the way to generate a digital signature is that you need a private key plus the message. And in Bitcoin, right, the message is the transaction. And then to verify those, you need a public key plus the message. Here's a graph to kind of visualize that Alice wanted to send this message to Bob, right? In the case of Bitcoin, this message will be Bitcoin. But basically, she signs a transaction with her private key. And now Bob and other people could verify that is actually from Alice using Alice's public key. So this solved the question of kind of like, how do you know if someone is spending their own Bitcoin, right? You have to use digital signature to prove the ownership of the Bitcoin. And by kind of signing a transaction, you're basically saying that you approve the transaction and the Bitcoin indeed belong to you. Now the second part is a Bitcoin transaction. So a quick example is, let's say Alice wants to send a transaction to Bob. So here's Alice and Bob. Here's Alice's Bitcoin. Here's her private key, and she wants to send some Bitcoin to Bob, and she do so by sending it to Bob's address. And now she put those information to a transaction and signed that transaction using her digital signature, and then sent that information to the blockchain. And here's the Bitcoin network that we'll get into in a moment, but the main purpose is basically to verify the transaction is in fact from Alice and that she has the Bitcoin that she claimed to have. And now after that is verified, now Bob can go ahead and access the Bitcoin sent from Alice by using Bob's own private key. Now, an interesting problem that people have been trying to solve is this thing called double spending problem, which is kind of like the ultimate enemy of digital money, right? You don't want to be able to spend the same money twice or more than once, right? And the way that Bitcoin solved this is by using this thing called UTXO. So on spend transaction output. And you can just think of it like a piggy bank, right? You have to spend all or none. You have to either break it or keep it. So here's a kind of illustration of it. There's two main parts contained in a UTXO. One is the value, the amount of Bitcoin, and then the other one is the owner address. So this piggy bank, this UTXO, has 5 Bitcoin, and these 5 Bitcoin belongs to this address. And one thing you are kind of realize is that Bitcoin is not account or balance based. So it doesn't keep track of how many Bitcoin you have. It's like you own these little piggy banks, you own these little UTXOs. So another example, Alice is trying to send 3 Bitcoin to Bob. So what Alice will have to do is, say she have a UTXO that has 5 Bitcoin, she has to break it, send 3 of them to Bob, and then 2 back to herself. Another example is, let's say Alice wants to send 7 Bitcoin to Bob. Now she has to break 2 piggy bank, 2 UTXOs, and a total of 8, and then spend 7 of it to Bob, and then 1 back to herself. And notice right here, the address is different for each one. So what these two are the same, but this one's different. So she changed her address, which is a secure way to do it. And now a more kind of realistic example is for Alice to send 3 to Bob, maybe 1.8 to herself, and then this 0.2 is something called a transaction fee that is sent to the miner. So miner is coming up in a couple of sections, but what a miner does is basically they verify the transaction. So you have to get them some kind of reward for it. And just some terminology here. A UTXO pool is basically a memory pool that stores all the current UTXOs. So it's basically used by miners to verify transaction. So you're able to see who owns what Bitcoin, and then be able to verify those Bitcoin are belonged by someone who's trying to spend it. Another terminology is transaction pool. So you kind of put all the current pending transactions together, and then the miners can go ahead and pick up some of them to verify. So a Bitcoin transaction example. Let's say Bob has 50 Bitcoin right here, and she wants to send Alice 0.5 of it. So now she sends 0.5 to Alice, and then the rest, 49.5, goes back to himself. And now Alice right here has 0.5 from Bob, and then along with 2 other people, some stranger or whatever, and then they together want to spend all those and then combine those payment into one and send to Alice's employee. So you can kind of see that you're able to break one payment down to multiple. We'll combine a few payments and then into one payment. So here's a way to kind of summarize it. You can read it afterwards. Yeah, some more information. Okay, so now we kind of know how to send and receive transaction, but how our transactions store on the blockchain. So we have to kind of go into what a miner does a little bit. So what miner does is they basically go to the transaction pool, gather some of the transaction they want to verify, and then verify it, and then put them into this block. Okay, but the way they put them into this block is by something called a Merkle tree. So I guess you can put it as a list, just put them one after another, but this is the more efficient way to do it. It's basically a data structure, a tree data structure, binary tree data structure, if you're I'm familiar with some computer science terms, but here's an example. So the leaf node, so the bottom ones are all the transaction data. So here's one transaction, here's another transaction, here's another, and here's another. And how this tree is constructed is basically first you hash each transaction. So here's the hash of the transaction one, here's hash of transaction two, and then hash of transaction three, hash of transaction four, right? And then going up from there, you kind of combine these two nodes. Hopefully you can see the drawing. Yeah. You combine these two nodes and then you put them together and then hash them again. So that's this block, this node, and then the same thing for the right. You put these two together and hash them. And then going up, you put these two together and then hash them to form this thing called the Merkle root, the root node. So, well, why do we do it this way? Because now a simple way to verify a transaction is you only need the Merkle root. You don't need all the data down here. You only need the root to know that if a transaction is inside this tree, if a transaction is contained inside this data structure. And here's another example, kind of in the opposite way, opposite approach. So the data is on top this time. Again, the data is basically transaction. And then you hash each one, right? Hash each one transaction, and then you combine them and hash them again. Combine them and then go all the way down to the root node. Now this root node kind of represent all the transaction on the top. So if you go ahead and change, let's say you change some data inside transaction D, then this will affect this one and it goes kind of ripple effect, and then the root hash will be different as well. So it's kind of a way to prove that no one changed the transaction data. So moving on to the network portion of Bitcoin. Now we kind of talked about this a little bit, but who verify those transactions? Miners verify those transactions. And we'll talk about what a miner is. So miner is basically people who do the work of mining. And in theory, everyone could be a miner, but what is mining, right? So basically a couple things. You first verify a transaction and then put them into a new block. And then this is an interesting thing, you solve a puzzle, which we'll get into in a bit, and then you publish this block to the blockchain. And that's how new blocks are created. And then one thing to note is that miners are in a race to compete who can publish a new block onto the blockchain first. And so for Bitcoin, about every 10 minutes, you can see a new block created. So every 10 minutes, the miner will gather all the transaction, put them into a block, solve a puzzle, and then publish it. So we talk about this, solve a puzzle thing, right? But what is it? A more formal name for it is called proof of work. And it's essentially the process of solving a cryptographic puzzle. Some of the properties are it's hard to solve but easy to verify. And the only way to solve it is by using brute force method, and consumes a lot of energy, as we'll see. So we'll go over example in a second. But for Bitcoin, what you do is you need to find a thing called nonce, and this stands for number only used once, such that the hash of the block results in a certain amount of leading zeros. And what we'll do right now is we're gonna do an example, a little demo here. So hopefully you can see it. Okay, so we talked about it last time, right? A hash is basically you have some data, and then each unique input will have a unique output. So Again, in the cases of Bitcoin, we have something like this, right? Sam sends some transaction to John, maybe like say 5 Bitcoin or something. And now this hash is a unique fingerprint of this data. And someone changed a little bit. So someone says change it to say 16. Now the hash is different. So they can't cheat that way. And now what a block is, now notice this block is green right now, right? But if I change anything, now it turns red. It's because if you see the hash down here, it starts with 4 leading zeros. So for the purposes of this demo, you can think of it as if the block starts with 4 leading zeros, then it's a valid block. If not, then it's invalid. So, you know, now because the data changed, the hash changed, now the hash doesn't start with 4 leading zeros, so it's invalid, so it's red. So now a block basically contains a block number, a nonce like we talk about, which we'll talk about in a little bit, and then some of the data, which is the transaction, and then the hash. So let's say I want this block to contain this transaction, right? And what do we do to make the hash starts with 4 leading zeros? Well, the way to do it is to change the data inside the block, but you don't want to change this transaction. So here, that's what this nonce is for. So what you do is basically you start with 0, and you see the hash just doesn't start with 0, and you change it to 1, and it doesn't start with 4 zeros. You go to the 2, you do the 4, 5, you keep going until you find one nonce, one number that could make the hash of this block start with 4 leading zeros. So that's basically what a miner do all day. If I click this mine button, it would try to find a number. So I found it. So this number will be able to make this block start with 4 leading zeros. The hash start with 4 leading zeros. And now, if I change the data again, say include another transaction, uh, 10 Bitcoin. Now, because I changed the data, the hash changed as well. I'm about to mine again to find a different nonce that's able to make this block start with 4 leading zeros. Hopefully this makes sense. If it doesn't, just ask me questions. So yeah, we're gonna go back to, here's a blockchain that we'll get back to a couple of minutes, but I want to go back to the slides for a little bit. Yeah, so hopefully you kind of know what I'm talking about when I say find a nonce such that the block hash has certain amount of leading zeros. So you're basically trying to find a valid block. And one interesting thing is that you're able to adjust the mining difficulty by changing the number of leading zeros. So if you have more leading zeros, then it's harder to get. If you have less leading zeros, then it's easier to find a nonce that matches that. Yeah, so here's another example. Just kind of briefly go over. So what you want to do is try and find a hash that's smaller than 2 to the 240th. So you have this data hello world, and then you put 10 after it, results in this number, which is not less than 2 to the 240th. And then you keep guessing 2, 3, 2, and then go ahead. And then finally at 4,250, now you're able to make this below the target of 2 to the 240th. So one question you might be asking is, why would people mine Bitcoin? Why would they spend all the electricity and the computational power to, find a nonce, basically solve the puzzle to create a valid block? Well, the answer is incentive, as you might have guessed. So mining incentive. So it is actually the only way that Bitcoins are created, and sometimes it's called Coinbase transaction in a block. And what it is basically if you create a new block, you get rewarded with Bitcoins. So back in 2009, if you create a new block, you get 50 Bitcoins. And every 4 years, the amount cuts in half. So since 2012, you only get 25 Bitcoins when you create a new block. And then now in 2020, you get 6.25 Bitcoins when you create a new block. And that kind of cut in half happened on May 11th of 2020. And the reason why they cut the amount in half every 4 years is because there's a fixed supply of Bitcoin. So there's only 21 million Bitcoins that could be created slash mined. And the last Bitcoin will be mined in the year of 2140. So if you look at it kind of in the graph, the supply of Bitcoin caps out at 21 million. But that also means the inflation rate of Bitcoin decreases over the years. So kind of summarize, the way that you mine a block is you download the entire blockchain, you verify transactions, you put verified transaction into a block, and then you find invalid knots. Basically mean you solve the puzzle, also called proof of work, and then you broadcast your block to other miners, other nodes, and then you hopefully make a profit out of it. Now going back to the demo, I want to finish the rest of it. Let's see. So we did the block. Now it's a blockchain. Okay. So notice now every block starts with 4 leading zeros, right? That's why they're all green. So now let's say I want to change the data inside this block. So I want to change it such that it include the transaction that I sent, right? So now this turned red because it doesn't start with 4 leading zeros. But notice is that each block has a parameter that's previous hash. So this one point is the same as this one, right? You can't draw on this, but basically this previous hash is the same as the hash of this block. And once I change the data inside this block, the hash of this change, right? It doesn't start with 4 leading zeros anymore. And that also changes this one, which matches this one. And because I changed the data inside this block, now the hash of this block changed as well. Okay. Let's try to finish this. Yeah, so this no longer start with 4 leading zeros. And then you can kind of see that continues down the row, right? So what you need to do is you mine this block. Now it does start with 4 leading zeros, and then you have to mine this block again and mine this block again. Then distributed blockchain is basically you give the same copy of blockchain to multiple people. So even if one trying to lie and then modify the data inside, and they're able to make sure that all the blocks are valid by, mining it, their data still doesn't match the one the others have. So people will know that they changed the data inside the blockchain. And a token way to express this is basically you have, instead of data, you have transactions. So kind of similar to what we did, you have the amounts and then from who to who, right? And then same thing over here, you still have the nonce. You still have the previous transaction parameter, and then you have the hash of the block. So again, if you want to change, let's say we want to mess with the transaction. So instead of 725, we said send 100, and then this block is no longer a valid block. So we have to mine it again, but that also means you have to mine the rest of the blockchain. So that's what makes it hard to change the data inside a blockchain, because not only you have to start from the block that you change and you have to go all the way to a current block. Even if you do that, your data won't match the other people's data. So it's basically impossible for you to change the data recorded on the blockchain. And finally, a coin-based transaction. So a more advanced way to express a block is, again, you have the block number, the nonce, but you also have a coin-based transaction. So basically, who created this block put their address here, and then they receive some certain amount of Bitcoin. And then you have the transaction data, and then same thing, previous hash, and then the current hash. So that is basically what a blockchain looks like. And so kind of talk about the evolution of Bitcoin mining. So you can kind of imagine that a lot of people want to get this Bitcoin, right? They want to make some money out of it. So back in 2009, Satoshi, the creator of Bitcoin, was able to mine Bitcoin using his laptop, so CPU. And then people quickly realized that, once more people wanted to mine Bitcoin, they realized that GPU actually performs better. So they started to use GPU. And then some people then put a bunch of GPU together and then started mining Bitcoin using that, which is more efficient, right? And then people started to create unique hardware called ASIC to the purpose of this hardware is to mine Bitcoin. And now they put a lot of ASIC together, and then this is what it's called a mining farm, a facility that exists to mine Bitcoin. So, like I said before, theoretically you can mine Bitcoin, but now the situation is you have to compete with mining farms, which is now is basically impossible for you to mine Bitcoin using your laptop. And as a result of mining, there's a lot of energy consumption, right? There's a lot of computational power, which requires electricity. So you can see that Bitcoin actually consumes a ton of energy, even more than some of the country over here. So that's one of the maybe downside of Bitcoin is the environmental effects. And then finally, we're going to get into Bitcoin blockchain. So a simplified way of a Bitcoin block basically have a few components, right? You have the block header, and then the Merkle tree. So a block header, you have the previous hash, so the hash of the previous block. You have the nonce, the puzzle you're trying to solve, and then the root of the Merkle tree. So, and then you have the data, all the transaction at the bottom, and then it goes up, and then you have the Merkle tree over here. A more detailed information for a block, again, you have the hash of the block, you have the previous hash, and then you have some timestamp parameter, you have the nonce, you have the Merkle root, you have all the transactions, and all the a lot of other informations that we won't get into at this moment. So there are mainly four types of users for Bitcoin. There's we talk about these two. So there's miner, basically they verify transaction and create a new block. And there's wallet, basically users who interact with the blockchain. So you spend or receive Bitcoin. There's also a full node that basically hold and distribute a full copy of the entire blockchain from the Genesis block. So the Genesis block is the first block of the blockchain. And then what a full node does is it stores all that in their memory. And then there's another thing called light node. They only store the block headers. So they were able to verify the authenticity of the transaction. So they only stored this part right here. And because they have the Merkle root, they're able to verify the transaction, but they don't have all the details. So what they do is if they need more information, they just ask the full node for more information. And in most cases, miner also are a full node. Just it's easier to do it that way, but it doesn't have to be. And a visual way to see it is a full node basically have the entire block that we talk about. They store all these things. And a light node only stores the block header. So like this. And then if they need more information like this to verify specific transactions, then they could ask the full node for more information. And okay, here's another demo that I wanted to show. Try to make it quick. So this is okay. So this is kind of interesting. This is the block that was last mined for Bitcoin, and this is the Bitcoin blockchain in real time. So each ball that drop is a transaction made, and then so the size is proportional to the amount of Bitcoin sent. So you can see, let's say, click on one, and then you have the transaction hash. You have the value. So this one has this amount of Bitcoin being sent. The mining fee is this amount. The timestamp, and then the input, the people who are trying to spend it, and then the people who receive Bitcoin. So in this case, one people trying to spend it, and then they spend it to two address. And you can see it, you kind of visualize it in real time, which is pretty cool. Okay, how much time? So yeah, Bitcoin's value. So essentially, the way I see Bitcoin is, or many people see Bitcoin is, you have a couple thing. You have this distributed network of nodes, which is this block right here. All the full nodes are part of this, so they talk to each other, and then they figure out a consensus that the state of the blockchain that they agree upon, and then other people like regular user are able to access and send Bitcoin through them. So by themselves, they're a distributed network, but as a whole system, Bitcoin is a decentralized system. And then the value of Bitcoin. So basically, the way I see it is that you can summarize Bitcoin blockchain in a way that is basically an immutable transaction database. So once the transaction is recorded, nobody could change it. And then it's a distributed network of nodes like this that communicate with each other. And then the value of Bitcoin is essentially is a decentralized payment system. Again, it's because it's immutable, and then it's digital asset with real value, and then a digital currency without boundaries. So people everywhere can still use Bitcoin. So that's the homework for today. If any question, could ask me. So yeah, that's the whole lecture for Bitcoin. I hope you learned something. Yeah, ask me if you have any questions. Thanks for listening.